Good morning, class. Welcome to the next video installment of Dr. Jordan's World of Math. This is section 4.5, part 2. Oops, can't spell today. So if you got through part 1, we talked about various forms of exponential equations. Today we're going to be talking about logarithmic equations. So let's go ahead and get started with an example from the homework. Example number 1. The ln of x is equal to 6. Now, in the previous section, we had sort of choices. We could use the natural log, the common log, or the base of the exponential that we were given. However, with logarithmic equations, you only have one choice, and that is whatever you are given, that is what you need to use in order to eliminate the logarithm. So if you're given a natural log is implied to be a base e. So we are going to raise both sides as exponents, base e. So the left-hand side now reads e to the ln of x equals the right-hand side is now e to the 6th power. Using a property of logarithms from the section 4.4, we have that e to the ln of x is equal to x. You can refer to that from section 4.4. So the left-hand side just becomes x, and our solution is e to the 6th power. And yes, it really is that simple for now. Some people like to actually see the exponential and the logarithm cancel out. So if you're one of those people, you like to cancel out the variable, the base and the logarithm, go ahead and do that, and that brings your variable down. It's kind of like when you cancel a square and a square root, you get that type of behavior. So this is the basic technique of solving a logarithmic equation using the proper exponential base. In my next example, we'll do base 10. So log of x is equal to 4. It is implied that this is base 10. So, similarly, we are going to raise both sides to the base 10. It's as if your equation is an equation of exponents. So the log x becomes the exponent on the left-hand side, the 4 becomes the exponent on the right-hand side. Similarly, the same property, applies from section 4.4. 10 log x is just equal to x. So on the left-hand side, we now have x is 10 to the 4th power. And again, if you like to cancel these out to make it look like they are actually interacting with each other, you can go ahead and do that. Last time we had an answer of e to the 6. That would be the exact value. So I just left it as an exact value, and I didn't bother using a calculator to approximate it. If you wanted to approximate it, of course, you could use your calculator here. And you could say e to the 6th power. I know I'm kind of going backwards here. This is for the previous example. It would have been approximately 403.4. Let's just do 2 decimals for this one. 403.43 would be my rounding for that one. Now, this type of rounding is common with an e because e is, born a decimal, 2.71. But with something like 10, no calculator is necessary. 10 to the 4th power is just 10,000. So we get the exact value either way. No calculator needed. Okay. So that's the basic idea. When we're doing exponentials and I ask for the exact value, give me the unsimplified exact value. If I ask for the approximate value, then use a calculator if necessary. Okay, moving right along. Example 3. So we have 9 halves log base 2 of x is equal to -6. An important technique is to isolate the logarithm first. Treat the entire logarithmic expression as the variable for now. So we really want to get rid of this 9 halves. So we're going to multiply both sides by 2/9. And that'll give us 18/18 or 1. I'm not going to write it. If you want to, you can. This is actually a 1. Go right here. I don't like to write it because it looks like a pair of L's if I write a 1. So I'm just going to imply that there's an invisible 1 right here. And so now over here, we're going to simplify this. This will be -12/9, or I like to simplify that a little bit more if possible, -4/3. Okay. Now we're ready to raise the roof. In other words, turn this into an exponential equation, and you must use the appropriate base. You don't have options in this business. So if the original problem is base 2, you need to raise everything to the base 2 exponential. Okay. So, same property again here. We have base 2, we have log base 2. Those are just going to cancel each other out, and we're going to end up with x. And now we have to interpret this. This is quite a complicated little expression here. This is a reciprocal, because it's negative. It's a 4th power. The numerator is the power. And it's a cube root. So we have 1 over the cube root of the 4th power of 2. In other words, we have 1 over the cube root. Now we can break this up. We can make this 2 to the 3rd times 2, just breaking up the 4th power as 2 to the 3rd and 2 to the 1. And now we can extract one of the 2's, and that would be our simplified power. I'm not going to require you to rationalize the denominator like you might have in other courses. For this particular application, leaving your answer in that form is fine. I would also accept, just jumping straight to the argument of 32, excuse me, 16. I overshot my mark. 2 times 2 times 2 times 2 is 16. I would also accept 1 over the cube root of 16. I'm not sure if you can see that. I think it went off the screen. Also correct would have been 1 over the cube root of 16. Okay. Next example. Example 4. 4 log base 3 of x plus 1 equals 0. All right, let's do it. So again, we want to isolate this. We need to get our 4 isolated. So we're going to divide both sides by 4. Don't panic. 0 divided by 4 is just 0. I've seen a lot of people panic when they get to that step. All right. It's going to have a trivial answer, as I can see here. We're going to raise both sides, base 3. There's that property again. We have the base 3. We have the log base 3. Those are going to cancel each other out. We're going to have x plus 1 equals 1. Remember, 3 to the 0 is 1. And we did all that work for nothing. Well, not for nothing. We got something out of it. Our solution is 0. Let's try another one. That one was just too trivial. So moving right along. Example 5. Maybe this one will work out a little bit nicer. Negative 3 ln of x plus 4 is equal to 9. This one will work out a little less trivial. So again, we want to isolate the ln. So we need to get rid of this coefficient here. We're going to divide both sides by negative 3. Now we have to use the base that's given. So we have natural log, so we're going to use base e. Both sides base e. The exponential and the logarithm are going to cancel out, and we're going to get x plus 4 equals 1 over e cubed. Might as well just do all that in one step. Finally, we're going to isolate our x, subtracting 4 from both sides. So we have x is 1 over e cubed minus 4. This would be the exact value. If you needed an approximation, I would do the 1 over e cubed first. So we could do... So that's 1 over e cubed. 0.04978, and then minus 4. X would be approximately negative 3.9502. And again, I think you're getting off my screen here. I really need to get a better whiteboard. I'm going to Staples today, okay? Hopefully they're open. One comment on how I did the exponential. I found it actually easier to do e to the negative 3 on my calculator. So I just did negative 3. Now be careful with negatives. It's not the minus sign on your calculator. That's subtraction. You have to use this one down here. This little plus or minus button here. This one right here. And that turns it into a negative 3. And then I do the e. It's much easier than doing 1 over e cubed, but you should get the same value either way. And then I subtracted 4, and that's how I got my approximate solution there. Okay. All right, next example. Example 6. Yeah, you guys aren't really there to help me keep track of these things, are you? Log base 2 of x plus log base 2 of x plus 1 is equal to log base 2 of 4. Yeah, I think I got a little bit off track yesterday because I don't have my students. I really need you guys to keep me focused and let me know if I missed an example number or something like that. All right, so for most of these examples coming up next, for the second part of this lecture, we're going to have to use a combination of properties. So the first property we're going to use is the sum to product property. So we're going to turn this sum of 2 logarithms into the product of 1 logarithm. 1 logarithm with a product of the arguments, if I want to say it properly. Okay. We might as well go ahead and multiply these now. So we're going to multiply them eventually anyway. So we're just going to multiply those and get x squared plus x. That way it just looks like one argument. Okay. Again, I'm using parentheses around my argument mostly for clarity so that that doesn't accidentally look like 24 or this doesn't look like, 2x or something like that. It's really just for clarity. If you're really careful about it, you can do stuff like this. I know people that do that. In fact, I sometimes do it. But in this particular context, seeing as that we're so far apart, I want to just be as clear as I possibly can. All right, so we have base 2 on both sides. Base 2 implies that we need to use base 2. Now here's a little trick if you want to save space. You can just put a big, giant 2 right here, and now you don't have to copy that entire line all over again. I love that trick, especially when I have such a small workspace here. So now I can cancel these logarithms and the base 2. It's very similar to what we were doing yesterday, just the reverse process. Notice we're never going to go back. So once we achieve a polynomial or some other type of simplified equation, we're not going to go back and revert it back to a logarithm. What we will do at some point is check our answer. I usually save that until the application section when I want to make sure that our answers make sense. For this particular presentation, if I start slowing myself down with that, we might never get there. So. Okay, so we got x squared plus x equals 4. This looks like it's not going to be factorable. Let's give it a try, though. I don't think it's going to be factorable. So we have x squared plus x minus 4 is equal to 0. I can't think of two numbers that multiply to be negative 4 but add to be positive 1. Can you? No, it doesn't look like we're going to be able to get that. So our options are either to use the quadratic formula or completing the square. What do you prefer? Do I hear quadratic formula? Okay, let's go for it. So x is going to be negative 1 plus or minus the square root of negative 1 squared minus 4 times 1 times negative 4 all over 2 times 1. Negative 1 plus or minus the square root of 17 over 2. Now, I'm not going to actually plug these numbers in. This is two values. But I am going to check with the domain here. The domain is x must be greater than 0 and x plus 1 must be greater than 0. Therefore, x must be greater than 0. So both of these values must be greater than 0. Okay? I can clearly see that one of them is not. Right? Negative 1 minus the square root of 17 over 2 is less than 0, so it's not in the domain. That value is not in our domain. So we do not get two values. We are only going to get one solution. Because our solutions must lie in the domain of the logarithmic function that we started with. So your only solution is negative 1 plus the square root of 17 over 2. Or if you want to get an approximate value, we'll do the square root of 17 plus negative 1 divided by 2. And so x would be approximately 1.5616. One point 5616. And that's correct. Want to try another one of those? Sure you do. So keep this in mind. With logarithms, logarithms have a restricted domain. You have to look at the domain of the arguments here, and you take the intersection of the two. So x is greater than 0 and x plus 1 is greater than 0. In other words, I didn't show this earlier, but x plus 1 being greater than 0 means that x is greater than negative 1. So if x is greater than 0 and x is greater than negative 1, that implies that x is just greater than 0. Maybe in the next example, we'll do that right from the beginning. Start to lose count. So log base 3 of x plus log base 3 of x plus 2 is equal to 2. All right. Why don't we just do the domain now? We'll do it over here on the side. X must be greater than 0. And x plus 2 must be greater than 0. So x plus 2, x must be greater than negative 2, and x must be greater than 0. All right. So you can think of that as a number line. Here's your x number line. Here's 0. Here's negative 1, negative 2. So we have two things going on. We have x must be greater than negative 2, and x must be greater than 0 at the same time. So if x must be greater than -2 and x must be greater than 0 at the same time, well then clearly the domain is from 0 to infinity. So we're not going to allow any solutions for this greater than, less than 0. All of our solutions must be greater than 0. You could do that at the beginning, or you could just wait till the very end when you get your final answer and then check it that way. It's really up to you. I'm afraid that I'm going to forget like I did last time, so we caught it just in time. Combine the logarithms using the sum to product property. These two logarithms combine into a product. That's a sum. Let's go ahead and distribute that. X squared plus 2x, just using the distributive property. Notice there's no logarithm on the right-hand side. Last time there was a logarithm on both sides. That's okay. It's okay. We're still going to use the same property. You'll notice what happens, though, when we use this property now, since there's no logarithm on the right-hand side is going to change. It's not going to stay at 2. So let's go ahead and raise the roof. We got 3 log 3 x squared plus 2x equals 3 squared. See, there's no logarithm on this side. So the right-hand side is going to become 9. But the left-hand side does have a logarithm. It's got a logarithm base 3. So those are going to cancel out. So now we have x squared plus 2x equals 9. I think we're going to end up in the same boat as we did last time. Very, very rarely do these come out factorable. If I ever get a factorable one of these, it means you got really lucky. So let's just go ahead and complete the square now, all right? I'm just going to leave it. I love, whenever I have a middle term, I think I've mentioned this earlier in the semester. If the middle term is even and the leading coefficient is 1, that is just crying out, complete the square. It's the best way. It's like saying, look at me, I'm already almost factorable. All you got to do is just give me that little push. All right, and here we go. The final result, we're going to square root both sides. We're going to have x plus 1 is plus or minus the square root of 10. Subtracting 1. X is -1 plus or minus the square root of 10. Check with the domain. All right, domain must be positive. -1 minus the square root of 10 is less than 0, so it's not in the domain. So we're going to throw that out, and we're going to keep only our positive solution. X is -1 plus the square root of 10. With your calculator, I would do the square root of 10 first. Square root of 10 is 3.16 plus -1 gives us an approximate value of 2.1623. So it's good to have both, approximation and an exact. For general purposes, approximations will be used mostly in the application section, although there are a few problems in this section that ask you to approximate it, mostly just to get you to practice using your calculator. I'd say, 90% of the problems in 4.5, you can just type in the exact answer and it should mark it right. If you don't see any instructions one way or another, just assume that the exact answer would be acceptable. So what do we got next? A couple more of these. Here's an interesting one. Example 8. What I like about this problem is it almost looks like a property. In fact, if you were to just tell somebody this is a property, we'll call it the distributive property of logarithms, but this is definitely not a property. If this were a property, it would be an identity, which means it would be true for every value of x, which means I really wouldn't be solving this equation, because we don't solve properties because properties have infinite number of solutions. They're identities, essentially. They're always true. At least they're always true within the domain. But this does have a solution. It has only one solution, or maybe it has one solution. Well, let's dig into it and find out what happens. There's nothing you can do on the left-hand side. The left-hand side is done. Log of x plus 12. You are done. All right. However, the right-hand side, you can use the product property. And you can multiply these arguments together. I know that kind of looks funny the way I wrote it, so in my next line, I'm going to just write it the standard way, 12x. It's x12. It's not typically the way we would write that. All right, we don't see a base, so we're to assume that the base is 10. Let's use our trick, saving some space here by just writing a big 10 here. Canceling out the 10s and the logs, giving us an ordinary linear equation, x plus 12 equals 12x. So this is a linear equation. It has one solution. I actually like to solve this one backwards, moving the x to the right-hand side, which I normally don't do, but every once in a while. So I get 12 is equal to 11x. All right, 12x minus 1x is 11x. And you see the last step is to divide both sides by 11. And we get an exact value of 12 11ths. I wouldn't bother approximating it. It's a repeating decimal. 1.0909090909. Let's just leave it as 12 11ths. Just a couple more examples and we'll be done with this. And then the fun part, word problems. Oh! I'll probably spend a couple days on the word problems, and we're going to have a test online. But let's just handle one thing at a time for now. This is a subtraction of logs. So remember, for a subtraction, it becomes a quotient. The difference of the logs is the quotient of the arguments. The difference of the logarithms is the log of the quotient. That's another way to say it. We got another base 10 problem here. It's base 10, so we can raise both sides. Base 10, base 10. We get x plus 5 over x plus 2 equals, now be careful here, this is 10 to the 1, so that's 10. It's not 0, it's not 1, they don't cancel out, it just becomes 10, 10 to the first power. Alrighty, rational equation. We need to get rid of the denominator, or at least move it to the other side so we can solve for x. So let's go ahead and multiply both sides by x plus 2. That will clear out our denominator here, give us a much easier equation to solve. And don't forget your distributive property. And finally, we'll just isolate the value of x. So we Whichever way you want to go, it really doesn't matter. Hey, I went backwards last time. Let's do it again. That seemed to work out pretty good for us. I refer to this as backwards only because I'm right-handed. And maybe if you're left-handed, this doesn't look backwards at all to you. It just looks normal. So we're going to get negative 15 equals 9x. We're getting off the screen here. Yep, getting off the screen. Divide both sides by 9. Come up here where you can see it. And you're going to get negative 15 ninths. Now this can be simplified. These are both divisible by 3. So I want the simplified answer, negative 5/3. I'm not sure what would happen if you typed in negative 15 ninths on Canvas. I know if it was on a paper test, I'd probably give you a small penalty for that. But why don't you just follow good etiquette and reduce whenever possible. So 15 divided by 9, or negative 15 divided by 9 reduces to negative 5/3. And again, we would have a repeating decimal. It would be negative 2.66 or 1.666666. Negative 1.66666666. All right, class. Only one more example, and we've gotten through these. I didn't have anybody on Confer Zoom yesterday, so for the office hours. So I don't know if that worked or not. We'll try it again today. But let's see how I get the lecture uploaded first, and let's see if you guys have any questions. Okay, we got one more example. 4.5, last example. Log base 7 of x plus 4 plus log base 7 of x minus 4 is equal to log base 7 of x plus 14. Now, one thing I want to make very clear before I finish this lecture. It is very tempting after you watch me do 8 or 9 examples to just pick out the piece that seemed easy. And I know for myself, when I was in this class, what the easiest part to me seemed was just putting the big 7 and canceling out the logs. And so you might be tempted to do that now. Don't do that, because if you try to just put a big 7, a big 7, and a big 7 and just kill the logarithms right now and make it a simple problem, you will not get the correct answer. You got to first use some properties. There's always at least one property involved here. So this is back to the product to sum to product property. So the sum of the logarithms is the product of the arguments. You must have one logarithm before you can use that property. You can have one logarithm on one side, you can have one logarithm on each side, but you cannot have 2 logarithms on the same side. All right? You can have at most one logarithm on each side of the equation, at most. Right, now you can do the big 7. Raise both sides to the base of 7. Notice that we're just using the 7 as a tool. All right? The 7 is just helping us kill the logarithm or cancel out the logarithm. It plays no part in the final answer. I'm starting to feel a little bit paranoid that I didn't check my last few answers. I'm just confident that everything would be okay. Maybe on this one, since it is the last example, we'll do a quick check to see if it's right. So now the logarithms are gone. We have an ordinary linear equation. Let's get rid of all these parentheses. This is a special product here, x minus 4, x plus 4, so x squared minus 16. Okay, let's set this thing equal to 0 and hope for the best. So all of this is going to cancel out. We're going to get 0. Over here, we're going to get x squared minus x. Now be careful here. This is a negative 16, and this is a negative 14. So that's negative 30. All right. Oh, we got lucky. You know what? If you stick around, you be patient long enough, one of these days you will get lucky. X minus 6, x plus 5. Don't you love that? Didn't have to use completing the square or the quadratic formula. All right, we're going to get two solutions. Let's see. We got x is equal to 6. X is equal to negative 5. These are our candidates. They might not be right. I don't know if you guys can see that. I keep getting off the board here, so let's see. X equals 6. X equals negative 5. These are our candidates. They might not both be correct. The last couple examples, I got a little sloppy with the domain. I'll leave that to the students to check. Maybe I did that intentionally. I didn't really. It was just a mistake, but that's okay. I'm not going to re-record this whole lecture. So what do we have? We have 3 different subdomains that we need to find the intersection of. So we have x plus 4 is greater than 0. So that means x is greater than negative 4. And we have x minus 4 is greater than 0. So that means x is greater than 4. And we have x plus 14 is greater than 0. So x is greater than negative 14. All right, we need to intersect all 3 of these things at the same time. So what do we have? We got negative 14, we got negative 4, we got 0, we got 4. So we got x is greater than negative 4. I brought some other colored pens for you guys today. I got x is greater than negative 14. You could probably have done this mentally, but what the heck. I got the colors, and I got x is 4. And I want all 3 of these at the same time, so clearly this is the winner. So our domain is that x must be greater than 4. So all 3 of these have to be simultaneous. All right, which one of these solutions is greater than 4? Only x equals 6 is greater than 4. So that is our one solution. The x equals negative 5 doesn't quite make it. It fell into this domain. It is greater than negative 14, but it has to be all 3 of them. It must satisfy all 3 of the original arguments. Remember, if a solution does not satisfy the original equation, it is not a solution. It's what we call a candidate or an extraneous root. All right, kids. Send me an email, post your comments and feedback. I'm going to try and get the Confer Zoom up and running again today. Perhaps the link didn't quite stick yesterday or whatever the problem might have been, or maybe you just didn't get around to checking in with me. That's okay. If you don't have any questions, then just keep calm and carry on. Have a great day.